here are some of the trig identities. These are the quotient / reciprocal identities. These four are the ones I think we use the most. The tangent is sine over cosine, the cotangent is cosine over sine, the secant is 1 over cosine, and the cosecant is 1 over sine. But these other four are also trig, or quotient or reciprocal identities that we sometimes use. Sometimes you'll see, like, really, I don't think you're ever replacing cosine with 1 over secant. I think what's more likely to happen is you end up with 1 over secant, and then you're like, oh, that's cosine. So that's kind of the way you might use these bottom ones a little bit. All right. We have a few others as well. We also have some Pythagorean identities. Again, this is all stuff I said last Thursday. I just think it bears repeating. And again, they're called Pythagorean identities because they literally come from using the Pythagorean theorem in a right triangle. So we have the following. We have everyone's favorite trig identity, or the most famous trig identity, is like what I call it. Sine squared theta plus cosine squared theta equals 1. And then from this, there's a couple other ways we like to rewrite it. Sometimes we like to write sine squared theta equals 1 minus cosine squared theta. Sometimes we like to write cosine squared theta equals 1 minus sine squared theta. And while I'm at it, even though this isn't in my notes, I will point out, because this does come up somewhat often, 1 minus cosine squared theta, you could factor this as 1 minus cosine theta times 1 plus cosine theta. And similarly, 1 minus sine squared theta, you could factor that as 1 minus sine theta times 1 plus sine theta. Sometimes that is useful information. And then we also have a couple other Pythagorean identities. We have that 1 plus tangent squared theta equals secant squared theta. Or as I will say over and over again, I tan and get sexy. It's just unforgettable. I know. You don't want to hear a teacher say that. I don't really tan, by the way. Also, I more burn and don't get sexy. So yeah, stay out of the sun. Good skin health is important. Wear sunscreen, all that stuff. Also, sometimes we do rewrite this one as tangent squared theta equals secant squared theta minus 1. And I guess you could write it as secant squared minus tangent squared equals 1, but that is just less typical for whatever reason. And then we also have the other version, 1 plus cotangent squared theta equals cosecant squared theta. Or alternatively, cotangent squared theta equals cosecant squared theta minus 1. This one you should definitely know, and these versions of it you should definitely know. These last couple, I would say of all of them, this is the one you probably want to know the most. If you're eventually going to take Calc 2, this one comes up a whole heck of a lot. This one less so, but a little bit. I mean, I'm gonna want you to know all of them, but if you're talking about which ones are more important, this is the most important one. This one's kind of important. The rest of it are like, eh. Okay. All right, so all that stuff we said last time. So now, I will also say I posted a couple videos of me doing some examples of this already. I'm going to show you some more examples, just how you simplify trig expressions using the identities. And I will also mention that there's usually no one right way to do these. There are usually multiple ways of kind of getting where you want to go. So I will try to show you the way that I think about it, and maybe another way of doing it, but really, if you can get there some other route, that is fine. I'm just trying to kind of encourage efficiency, I suppose. So we're going to use the following. We're going to use the quotient and Pythagorean trig identities to simplify the following expressions to a single term. So here's the first one: sine of theta times 1 plus cotangent squared theta. So I want to simplify this down to one term. And there's a couple ways to go here. I'm going to show you two ways for this one because I think some people just think differently. That shouldn't say cosine. I know I said cotangent squared. I wrote cosine squared. Sorry about that. I should say cotangent squared theta. So one way to do this would be to remember the identity for 1 plus cotangent squared. And say, oh, sine theta times 1 plus cotangent squared theta is equal to sine theta times, well, 1 plus cotangent squared is cosecant squared. That's one way we could start. And then my usual go-to kind of thing is if I see cosecant or secant or tangent or cotangent, I often think I'm going to rewrite that thing in terms of sines and cosines. So I'm going to rewrite cosecant squared. So actually, let me show what intermediate step. So if you want, you can skip this step, but you can say, well, cosecant squared is really just cosecant of theta quantity squared. And then cosecant is 1 over sine of theta. And so cosecant squared is 1 over sine of theta squared. And then I can rewrite this as sine of theta times 1 over sine squared theta. Yeah, because 1 squared is just 1 and sine squared is just sine squared. I think you could totally skip this step and this step and just jump straight to saying, well, if I know cosecant is 1 over sine, then I know that cosecant squared theta is 1 over sine squared theta. That is a perfectly fine step to take next. And then one of the words are failing me. This sine theta here and one of the sines here can cancel out, and we would have just 1 over sine theta, which we should then write as cosecant. Whoops. Cosecant of theta. So this trigonometric expression simplifies down to the one term, which is just cosecant of theta. That's one way we could go about doing this. Another way, which also seems perfectly legitimate to me, is the following. I'm gonna rewrite this up here just to give myself a little bit more room. I'm gonna erase this. So here's another way you could go. This is where my brain often goes, because I will be honest, I don't always remember that 1 plus cotangent squared theta is equal to cosecant squared theta. It's just one of the ones that doesn't stick inside my head. So I don't remember that. I'm going to say, well, cotangent squared, I'm going to write cotangent in terms of cosines and sines. So cotangent of theta is cosine theta over sine theta. So cotangent squared theta is cosine squared theta over sine squared theta. And then I'm going to get a common denominator so that I can add 1 plus this fraction. So my 1 here is going to turn into sine squared theta over sine squared theta. So I'm going to have sine theta times sine squared theta over sine squared theta plus cosine squared theta over sine squared theta. Also, hope you all had a nice weekend. I had a very lovely birthday. Thank you for the birthday wishes. I appreciate them. Had a nice time. A friend made me dinner. It was delicious. All right, so simplifying this here. So now that I've got a common denominator, I'm going to add these fractions, and I'm going to get my denominator is just going to be sine squared theta, and on top I'm going to have sine squared theta plus cosine squared theta. And while I don't always remember that 1 plus cotangent squared theta equals cosecant squared theta, I do always remember that sine squared theta plus cosine squared theta is equal to what? Everybody. Yeah, that's some of you. Okay, cool. Yes, thank you. Thank you for the everybody, for the few of you that responded. I appreciate it. Yeah, sine squared theta plus cosine squared theta is 1. So this becomes sine theta times 1 over sine squared theta. And then again, this sign here can cancel with one of the signs there. I get 1 over sine theta, which is better known as cosecant of theta. So either way you want to do this problem or some other way you want to do this problem is perfectly fine. These are the couple different ways I would kind of imagine it. My go-to kind of place is usually sines and cosines. All right, let's look at some more. Let me erase to the side of the board, and then we'll do another example. Okay, I should try to. I always use up my black pens too fast. They're definitely the ones I like the best, but I use them too quickly. So let me try and alternate between. There's another black pen. Maybe this one hasn't been all used up already. Oh, it probably has though. All right, let's take a look. So what's next on my agenda here? So my next problem is sine of x times tangent of x plus cotangent of x. I do want to emphasize, I didn't see too much of this on the homework, but I did see a few times where people wrote sine without an angle, or tangent or cotangent without an angle, or some variable for the angle. Whenever you're writing a trig function, whichever one it is, there always needs to be something inside the trig function, right? Just like it wouldn't make sense to write a square root without anything in it. It doesn't make sense to write a trig function without anything in it, right? So we don't want this. This is kind of like writing sine. We want the square root of x, which is like writing sine of x. Or the square root of, I don't know, 9, which would be like writing sine of 2 pi. And you always need to have an argument inside your function. This pen is less than excellent, though. Okay. So, sine of x times tangent x plus cotangent x. How did I think about this one? Okay, I thought that way, sure. So I'm thinking of this. I'm thinking I don't love this pen. Sorry, it's always hard to keep track of which pens have started to suck. Apparently all of these. I know I had a good green one around somewhere. This one. So I'm going to write tangent of x as sine of x over cosine of x. And I'm going to write cotangent of x as cosine of x over sine of x. And like the previous problem we did, I'm going to add these fractions together by getting a common denominator. So I'm going to write this as sine of x times sine over cosine. I'm going to multiply by sine x over sine x. And cosine over sine, I'm going to multiply by cosine x over cosine x. So that now each of these two terms will have the denominator cosine x times sine of x. Grab a drink of water. So let's see, sine of x times, so this is going to be sine times sine, which is sine squared. Cosine times cosine is going to be cosine squared. And the common denominator that they each have is cosine times sine. So cosine x times sine of x. And this is going to happen often. Again, we see that the identity sine squared x plus cosine squared x shows up, and that's equal to 1. This is going to be sine of x times 1 over cosine x times sine of x. We can certainly just cancel the signs right there, or if you prefer, you could multiply it to one fraction. So you can say, well, this is sine of x over 1. And then if we multiply fractions together, sine of x times 1 is just sine of x. 1 times cosine x sine of x is just cosine x sine of x. And then we can cancel the signs. But you get to cancel them over there. Either way, we get 1 over cosine x, which is secant of x. Your thing. Okay. Cool. Questions so far? I've got a couple more examples. Let's see. So let's look at this one. This one looks kind of tricky. Okay. So I've got sine of alpha divided by secant alpha minus cosine alpha. Okay. All right. Okay. So good question. I don't know. Good question, James. What to do here? I would probably rewrite secant of alpha as 1 over cosine of alpha. Again, my usual go-to is to rewrite things in terms of sines and cosines. So I see a secant or a cosecant or a tangent or a cotangent, I'm going to re-express it in terms of how it looks with sines and cosines. Now, there's a couple ways you could deal with this next part. One way would be to get a common denominator in your denominator, right? You could totally say this is cosine of alpha over 1 and multiply by cosine alpha over cosine alpha. And that would be perfectly fine. In fact, I think that's what we're going to do. So I've got sine of alpha over 1 over cosine of alpha minus cosine squared alpha over cosine of alpha, which I really should have just put together as one fraction in the denominator. I guess we'll do that in the next step. So this is sine of alpha over 1 minus cosine squared alpha over cosine of alpha. Before I do any flipping and multiplying, I'm going to change 1 minus cosine squared into sine squared. All right, that's a trig identity. So I'm going to write this as sine of alpha over sine squared alpha over cosine alpha. And then I'm going to multiply by the reciprocal. If I'm dividing by a fraction, I'm going to multiply by its reciprocal. This is going to become sine of alpha times the reciprocal of this. So cosine of alpha over sine squared of alpha. And then I'm going to write this as sine of alpha over 1. And I can cancel a sign here and one of the signs there. So I end up with just cosine of alpha over sine of alpha. And cosine over sine is cotangent. And then I have one more example in notes that actually turned out wrong. So I'm not going to do that one for you guys because it doesn't simplify down to one expression. Let's see here. Let me go over to the other side of the board. Okay. So there's a few more examples I have here, but they're all examples I've already done on video that's on Canvas, so I don't feel like it makes the most sense to repeat doing them. So I'm not. So let's do some verifying. So the other kind of thing we do with identities sometimes is we verify that they're true for a certain value. So for example, I want to verify that cosine squared theta equals 1 minus sine squared theta for a particular value. For theta equal to 4 pi over 3. So all that really means is I'm going to plug in 4 pi over 3 for my angle and check that whatever I get on this side and whatever I get on this side are actually the same. So I like to do it this way. I like to look at the left-hand side and the right-hand side separately and then see that they're actually equal to each other. Depending on how, sometimes I don't do it this way. I'll show you. There's a different example I have that it's different. So for the left-hand side, that's going to be cosine squared of 4 pi over 3. And in this case, it might make more sense to write it as cosine of 4 pi over 3 quantity squared. Right? This abbreviated notation isn't always the best notation for what we're doing. All right, cosine of 4 pi over 3. So I know my reference angle is pi over 3. I know my quadrant is quadrant 3. So I know cosine is negative in quadrant 3. And if my reference angle is pi over 3, I know cosine is the 1/2 value. So it's going to be negative 1/2 because we're in quadrant 3. So cosine of 4 pi over 3 is going to be a negative 1/2. So it's going to be negative 1/2 squared, which is going to be negative 1/2 times negative 1/2, which ends up being positive 1/4. Excuse me. So then what we have to do is we have to check that the other side, the right-hand side, ends up being the same. So we're going to do 1 minus sine squared of 4 pi over 3. Or if we prefer, 1 minus sine of 4 pi over 3 all squared. Okay, here's a thing that I remember is always true about sine and cosine. If one of the values of sine or cosine is a 1/2 or a negative 1/2, then the other one is a √3/2 or a negative √3/2. Right? Those two values always go together for sine and cosine, really because of the triangle. Let me show you, I'll come back to this, but just let me show you what I mean, right? Right, the triangle that goes with the angle pi over 3 is the triangle where this side is √3, this side is 2, and this side is 1. And that angle up there is pi over 6. So I know that if one of the values of sine or cosine is √3 is 1/2, right? So for example, here I can see that cosine of pi over 3 is 1/2, right? It's adjacent of hypotenuse. Well, then the other value, sine, has to be the √3/2 value. What I'm trying to say, using probably way too many words, is that these always go together. If sine is one of those values, cosine is the other one, and vice versa. Right? If I look at this angle up here, sine of pi over 6 is opposite over hypotenuse. It's 1/2. And cosine of pi over 6 is adjacent over hypotenuse, which is √3/2. So one of them is 1/2, one of them is √3/2. Always go together. And then we adjust whether it's positive or negative based on what quadrant we're in. So for this problem that we're doing on the other side, since we're in quadrant 3, we know both sine and cosine are going to be negative. So here's what I get. I get 1 minus negative √3/2 quantity squared. But when I square this, Negative root 3 over 2 squared is just 3 over 4. We could write out the multiplication if we really want to. It's 1 minus negative root 3 over 2 times negative root 3 over 2. And when you multiply this together, negative root 3 times negative root 3 is positive 3. 2 times 2 is 4. So you get 1 minus 3 over 4, which is 1/4. And those are the same. So then I like to make like a check mark. But yeah, I did it. It's what I want it to be. So this is an example of verifying that this trigonometric identity is true for this particular angle value. And this should work for any angle that is in the domain of the expression. So I could have picked pi over 4 or 5 pi over 6 or anything, and this should be true. It is true. We can show it's true. So, in fact, let's do a couple more. I keep going the wrong way with my board. I'm going to do it for 2 tight. So let's do the same. Well, let's just so let's verify that sine squared theta plus cosine squared theta equals 1 for theta equal to 5 pi over 6. Okay. So just to point out something I've been doing that maybe I haven't explained very well. So I'll do it after this problem. So the reference angle for 5 pi over 6 is pi over 6. And the quadrant is quadrant 2. So I know my cosine value is going to be negative, my sine value is going to be positive. But you might have seen me do this thing where, so I say my reference angle is pi over 6, and then I kind of do this. I kind of tilt my arm up at the angle I think about. Now there's a reason why I do this. I mean, it's kind of habitual at this point, but so here's what I'm doing. I'm thinking, okay, here's pi over 6. And this, sorry, am I oriented the way that makes sense? Am I going, do I look like I'm on the positive x-axis? And I point, to me I do, but I don't know. Does this look like I'm pointing to the right? Okay, good. Sorry, it's especially hard on video to know if I'm actually going the right way. So, right, so, you know, we go counterclockwise around the unit circle. And what I'm thinking about is, why don't I just draw the thing I'm thinking about? So pi over 6 is the lesser angle. Pi over 3 is the larger angle. And we know that sine and cosine, sorry, I should say cosine and sine, are respectively the x and y coordinates. So, right, this is cosine pi over 6, comma sine pi over 6. And here this is cosine pi over 3, sine pi over 3. So the reason I do this or this is because when I do this, I know that I'm going further out than I'm going up. So I know that my x value is larger than my y value because I've gone more to the right than I've gone upwards. Whereas if I do this, I know I've gone not very far out, but I've gone kind of far up. So I know when my angle is pi over 6, the x value is the larger value and the y value is the smaller value. When I've gone pi over 3, I know the x value is the smaller value and the y value is the larger value. And I know I only have 2 values to pick from. I have 1/2 or root 3 over 2. Right, when it's pi over 6 or pi over 3, I know those are the only options for sine and cosine. Okay, so now, if my angle is pi over 6, cosine is the larger value, which of these numbers is bigger? 1 over 2 or the square root of 3 over 2? So really the question is, which is bigger? 1 or the square root of 3? I know I didn't actually ask a question, but yes, it is the square. I know someone was just about to say it. It is indeed the square root of 3. So this is always the bigger one. And this is always the smaller one. So when I'm thinking about what cosine or sine of either pi over 6 or pi over 3 is, I'm really just asking myself, okay, is it the one where cosine is bigger or is it the one where sine is bigger? In this angle, the x is the bigger thing because I've gone further out than I've gone up. Cosine is bigger, so cosine is the root 3 over 2. And sine is the 1/2. Whereas for pi over 3, if I was doing pi over 3, I know that I've gone more up, so sine, the y value is the bigger thing, and x, the cosine value, is the smaller thing. So the whole reason I just spent a few minutes talking about that is hopefully that'll make it easier for you to remember which one is which. You're like, oh, pi over 3, well, that's the bigger angle, that's the larger y, the smaller x, so sine is the root 3 over 2, cosine is the 1/2. Okay, I think I've said enough about that, maybe. So in this case, the angle is pi over 6. I'm in this situation, so I know that cosine, so I know that cosine of 5 pi over 6 is the larger value. It's the root 3 over 2, but it's negative root 3 over 2 because I'm in the quadrant 2. And similarly, sine of 5 pi over 6 is positive 1/2. I'm not done, because I didn't actually verify the identity yet. So what I should actually be doing is I should be saying, okay, I want to verify this identity. I should say sine squared of 5 pi over 6 plus cosine squared of 5 pi over 6 equals, well, sine is 1/2. So it's 1/2 squared. Cosine of 5 pi over 6 is negative root 3 over 2 squared. 1/2 squared is 1/4. Plus negative root 3 over 2 squared is 3/4. 1/4 plus 3/4 is 4/4, which is 1. In this problem, unlike the previous one, since the right-hand side is just a value already, I would just start with the left-hand side and work on it until I got it to be equal to 1. Whereas here, I would actually do the left-hand side and the right-hand side separately. But for this one, it doesn't really make sense to work on the right-hand side because it's just 1 already. Okay. Now, like what, 12 minutes? Okay. Plenty of time. It's like my favorite thing to say because it's never true. I never have enough time. Okay. Let's do one more. There's one more I want to mention just because it's slightly different. So we want to verify that secant squared theta minus tangent squared theta is equal to 1 for theta equal to, what did I pick? 3, let's go 7 pi over 4. As usual, we're going to use the reference angles. So the reference angle here is pi over 4. The quadrant is quadrant 4. So in quadrant 4, tangent's negative. In quadrant 4, cosine is positive, so secant is also positive. All right, so secant, who picked secant? So I don't remember secant ever really. I know that cosine of pi over 4 is the square root of 2 over 2. So I know that secant of pi over 4, so secant of pi over 4 eventually ends up being just the square root of 2. You could flip this over and say it's 2 over root 2, and then you could do some work to rationalize it. I don't really want to do all this work, but you could do root 2 over root 2, and then the top would be 2 times root 2. The bottom would be root 2 times root 2, which is 2, and then those cancel and give you root 2. The easier way is just to say, oh, cosine was really just 1 over root 2, and if you flip that over, it's just the square root of 2. Or if you're doing 2 over root 2, any number divided by its own square root is just its own square root. Let me say that again, just to make sure everyone's cool with it. Any number divided by its own square root is just its own square root. So for example, like 7 over the square root of 7 is the square root of 7. And 2 over the square root of 2 is just the square root of 2. Okay, so secant of 7 pi over 4 That's going to be squared minus tangent of 7 pi over 4, also squared. Now let's see. So we just said secant of 7 pi over 4. Well, we said secant of pi over 4 is root 2. So secant of 7 pi over 4 is going to be positive root 2 because it's in quadrant 4 and secant is positive there. Tangent of 7 pi over 4, well, I know that tangent of pi over 4 is 1. So tangent of 7 pi over 4 is going to be negative 1 quantity squared. The square root of 2 squared is 2. And negative 1 squared is 1. And 2 minus 1 is 1. And it works. And again, these identities should be true for any angle we pick. Well, small little caveat here. This identity is true for any angle. This identity is true for any angle that you can take the secant or tangent of. But there are some angles that you can't take the secant or tangent of because they're undefined. So this is true always, but this, I would say this is not true for theta equal to pi over 2, for example. Because for pi over 2, secant and tangent both are undefined. So just be, and this is not a big deal. If you forget what I say right now, it probably will never matter. But you should just be aware that this identity isn't true if the angles make the trig functions undefined. Got a few minutes left, all right. So that's probably all the material that pertains to the homework assignment that's due tomorrow. I'm going to do an example that's moving on towards what we're actually going to talk about tomorrow, but I've got 6 minutes. I might as well use them. But I will probably end class on time today, for real. My wife was making fun of me yesterday because she's like, I know you're not doing this. Well, she's into it. She said, I didn't see you doing it, but by the way you're talking, I can tell you're doing like this. And she said, I was like, yeah, you're right. And totally, I'm like, yes, this and this and this. And I do sometimes. You might have noticed, sometimes I do that. Also, she cut my hair on Friday. I have a lot less hair. It feels good to have a lot less hair because I had too much hair. And it took forever to wash it. I know, like, in the world of hair, I didn't have that much hair. Many people have much more hair than I have, but it was taking me a lot longer to wash my hair than I am used to. All right, so here is, well, this is going to lead us to a couple new identities that are different than the ones we've already talked about. So we're going to verify that sine of pi over 6 plus pi over 3 is equal to sine of pi over 6 times cosine of pi over 3 plus cosine of pi over 6 times sine of pi over 3. This is the beginning of this is leading us to what's called the angle sum identity for sine, which we will definitely talk about tomorrow. But for now, let's do an example and see that it's actually true. So let's do the left-hand side first. Left-hand side is easy. Sine of pi over 6 plus pi over 3. I'm going to get a common denominator, right? So there's no way you can break this apart into two different things other than using this here. What I'm going to do instead is I'm just going to add those angles together. You could also think it, right, if you wanted to go degrees, you'd be like, oh, well, that's 30 degrees, that's 60 degrees, you add them together, you get 90 degrees, so it's pi over 2 radians. Or you could use fractions to add them together and say, well, that's pi over 6, and I'm going to multiply this by 2 over 2 to get 2 pi over 6, and then 1 pi over 6 plus 2 pi over 6 is going to give me sine of 3 pi over 6, but 3 pi over 6 reduces to pi over 2. So this is indeed sine of pi over 2. And then using our unit circle, using the 4 corners of the circle, There's the point 1, 0 at angle 0. Here's the point 0, 1 at the angle pi over 2. So is sine of pi over 2 0 or 1? Someone's like, I don't know, I'm leaving. I think someone just, yeah, 1. It is definitely 1, right? Because sine is the y coordinate. That's going to be 1. All right, now let's go the other way. Let's do the right-hand side. So the right-hand side is going to be all this mess. So sine of pi over 6, cosine of pi over 3, plus cosine of pi over 6, sine of pi over 3. And let's see here. So, again, using my tried and true arm method, sine of pi over 6, so pi over 6 is the small angle. Sine is the y value, so that's going to be the smaller of the two values. So it's not going to be root 3 over 2. It's going to be positive 1/2. So I'm going to get 1/2 here. Cosine of pi over 3. So pi over 3 is the larger value, but cosine is the x value, meaning it didn't go far out. So it's also the smaller value. That's also going to be 1/2. Cosine of pi over 6, that's the x value. It's the larger of the two, so it's root 3 over 2. And sine of pi over 3, again, the y value is the larger value for pi over 3, so it's also root 3 over 2. So, end up getting 1/2 times 1/2, which is 1/4, plus root 3 over 2 times root 3 over 2, which is 3/4, and that adds up to 1. So yes, it's true that sine of pi over 6 plus pi over 3 is equal to sine of pi over 6 times cosine of pi over 3 plus cosine of pi over 6 times sine of pi over 3. And here's what we're going to see more generally tomorrow. So this is the last thing I'll say. And we're going to have there's going to be a couple of these formulas, but here is the one we just showed an example of. That sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. So that trig identity, this angle sum identity, is true for any angles alpha and beta. And the neat thing about this, which you will see tomorrow, is that this is going to allow us to actually evaluate the trig functions of some new angles. So like for now, we've only really been able, without a calculator, to do angles like 30 degrees or 45 degrees or 60 degrees or 90 degrees. But now we can say, I'm going to use this, and I'm going to stop right here. We can use this to find, say, sine of 75 degrees, or if you prefer, sine of 5 pi over 12 radians. That's what we're going to do tomorrow, is we're going to use these angle sum and difference identities to evaluate sine and cosine of some new angles that we weren't able to before.